We're going to talk about the autoionization of water today. We've talked about how water is amphoteric. That means that it can act either as an acid or a base. There are many things out there that are amphoteric, but water is a really, really important one for us now that we are about to discuss aqueous solutions, solutions happening with water. About 2 out of every 1 billion water molecules form ions through a process called autoionization, where water splits into H plus, the proton, and hydroxide, OH minus. You can also think about it in terms of 2 water molecules doing a proton transfer where one is acting like an acid and one is acting like a base. So let's go ahead and just draw that out on that second reaction with some curved arrows. A base will come and use its lone pairs to pick up a proton on the acid. The covalent bond between that proton and the rest of the acid, namely here the oxygen, will break and become a lone pair on the conjugate. The base becomes the conjugate acid, H3O plus, or hydronium, and the acid becomes the conjugate base, or hydroxide. All aqueous solutions do contain both H3O plus and hydroxide in the solution. The concentrations of H3O plus and hydroxide are equal in water. So when we're looking at a pure water solution, the concentration of hydronium is equal to the concentration of hydroxide, which will be 1 times 10 to the negative 7 molarity at 25 degrees Celsius. Now, this leads us to a very, very important discovery, the Kw, the equilibrium constant for the autoionization of water. Let's bring that up again. We'll use the 2H2O. Liquid is in equilibrium with H3O plus, AQ, and hydroxide, AQ. Notice here a K, the equilibrium constant K, is going to involve, again, products divided by reactants, but because our reactant water is a pure liquid, the K for this autoionization is going to be expressed by the concentration of hydronium times the concentration of hydroxide. That we will give a special denotation of the Kw. The Kw at 25 degrees Celsius is always going to be 1.00 times 10 to the negative 14. Again, unitless value. If you measure one of the concentrations, you can always calculate the other with the Kw. So this value is called the ion product of water, and it has the symbol Kw. It's also known as the dissociation constant of water. So as H3O plus increases in a solution, the OH minus concentration must decrease so that the products stay constant. That means that the concentrations of hydronium and hydroxide are inversely proportional in an aqueous solution. All aqueous solutions contain both H3O plus and hydroxide ions just because they are in water. Neutral solutions will have equal amounts of hydronium and hydroxide. So each of those concentrations will be 1 times 10 to the negative 7. Multiplying them makes the Kw 1 times 10 to the negative 14. Acidic solutions, so once we start thinking about mixing an acid with water, acidic solutions will have a larger concentration of hydronium than hydroxide. Because we increase the amount of acid, water and the acid are going to react to form more hydronium than what is typically present with just the autoionization of water. So we'll see that acidic solutions are going to have a higher concentration of H3O plus. It will be greater than 1 times 10 to the negative 7. Basic solutions are going to have a larger hydroxide concentration, something that is greater than 1 times 10 to the negative 7 for the hydroxide concentration. we can utilize the Kw as well as other aspects of a specific reaction when trying to find the pH of a solution. Now, in measuring acidity, the pH is going to be that negative log of the H3O plus concentration. It can also be written as the negative log of the H plus concentration. H plus and H3O plus are interchangeable here. It's whether we chemists are being lazy or not, and we care about writing the whole hydronium ion itself. The exponent on 10 with a positive sign is really important to be able to note here that the exponent of that concentration times 10 to the whatever, it's really taking that value of concentration and making it into a manageable number. That's why we use pH. So as we saw before, if the concentration of H3O plus in pure water is 1 times 10 to the negative 7, punch that into your calculator. The pH is 7, a much more manageable number than 1 times 10 to the negative 7. That gets a little bulky. So the pH is really important to be able to express, and it can express acidity or basicity. All right, if the pH is less than 7, it's called acidic. If the pH is greater than 7, it's called basic. If the pH is equal to 7, we call that neutral, such as water. Water in its pure form has equal amounts of H3O plus and hydroxide. The concentration of H3O plus, therefore, is 1 times 10 to the negative 7. For a neutral solution, if we took the negative log of that value of concentration, we'd get 7. So being able to understand the concentration of hydronium in a solution will directly relate us to the pH of that solution. We can always go backwards as well. If you have the pH and you want to find the hydronium concentration, all you have to do is take 10 to the negative pH and you will get it back into the H3O plus concentration. This is also called taking the anti-log. Remember that taking the log of something is a logarithmic base 10 scale. So we are changing these values. So 1 pH unit change between 6 and 7 per se is really 10 times the change in acidity. All right. So looking over here at the table 16.6, some common things that we see. Lemons have a pH range of 2.2 to 2.4 versus something like, let's just take beers, 4 to 5. Now, even though that change in pH only looks pretty small, about 2 to 3 units, remember it's log base 10 scale. So it's really times 10 to the 3 units. All right. So about 1,000 times more acidic as lemons versus beer. All right. The pH number, again, the normal range of pH is between 0 and 14. That doesn't mean that we can't get lower or higher than this range, but this is typical. The lower the pH, the more acidic. The higher the pH, the more basic. 1 pH unit corresponds to a factor of 10 difference. So that's where we get to see the pH scale here versus the H plus concentration. So again, if something has a pH of 1 versus something that has a pH of 2, they're not really close, right? The pH of 1 is 10 times more acidic than the pH of 2. pH can be negative or larger than 14. It's just in more extreme cases that we see those values. pOH, what is the pOH? Why do we need it? Well, sometimes we want to express acidity and basicity with a pOH. A pOH is the negative log of the hydroxide concentration, right? So if you know the pOH, you can also determine the hydroxide concentration itself. pOH of water is still 7. We still have that hydroxide concentration for neutral pure water as being 1 times 10 to the negative 7 molarity. And so we can plug that in and still see that the neutral scale, 0 to 14 for pOH, is the same as pH. The only difference is how we read those values. A pOH that is less than 7 is deemed basic. A pOH that is greater than 7 is acidic. And just like before a POH equal to 7 is neutral. So it's just referencing what log base 10 scale are we looking at, basicity or acidity. The relationship between POH and pH is very important to note too. Just like the Kw is equal to the hydroxide concentration times the hydronium concentration, sorry, I said that backwards, and that is equal to 1 times 10 to the negative 14, the pH plus the POH is going to be equal to 14 at 25 degrees Celsius. If you know the POH, you can determine the pH, and if you know the pH, you can determine the POH. And again, remember, it's all based off of that Kw, the autoionization of water. It's very important to remember these two values, Kw and pH plus POH. All right, pKa versus pKb. Another way of expressing whether the strength of an acid or base is not only through the pH of a solution that it makes with water, but also through its negative log of its equilibrium constant. So the Ka, the acid equilibrium constant, remember when we talked about an acid mixing with water to form hydronium and a conjugate base, that Ka, hydronium, times conjugate base divided by acid can be also rearranged to have the negative log so that it again is a more manageable number. We saw that those numbers can get very, very small, times 10 to the negative 12, times 10 to the negative 15. In order to manage those numbers better, the pKa is utilized. Now remember, a large Ka then will convert to a small pKa, all right? Remember how we said the lower the pH, the more acidic? The lower the pKa, the more acidic. pKb, we can relate it just like we had the POH. It's a way to measure base strength, all right? And so when we're looking at very large KBs, those result in smaller PKBs. We'll talk about all of those references in class, but we want to get into some other ideas as well to be able to look at some values. So let's get into that. Percent ionization is another way to measure the acid strength, and it's determining the percentage of acid molecules that are able to react and ionize with water. So we call strong acids 100% ionization. They react completely with water. Our weak acids will not be doing that. This is where we'll get a smaller percent ionization. Weak acids do not like to react with water. So in order to figure out whether what the pH is of a solution, we do need to know a couple of different things. We need to know whether the acid is strong versus weak. If we have a strong acid will always 100% dissociate or 100% ionize. So that means the concentration of that strong acid is going to equal the concentration of hydronium because it completely ionizes in the solution. So if we had a, let's just say 1.0 molar HCl solution, all right, that literally means that we have a 0.1 molar H3O plus solution. So we can take that straight into our negative log of the hydronium concentration and find the pH, all right? Now, when we're doing this, what's really important for us, and we're gonna reintroduce sig figs. How do we take sig figs for the pH? And I think this is really important, especially for lab. The amount of sig figs in the concentration, which is here 2 for this example. becomes the number of decimal places in the pH value. The reason for this switch in types of sig fig calculation is because of the log base 10 scale. So again, the number of sig figs in the concentration is going to be equal to the number of decimals in your pH answer. The only one of our strong acids to be really, really careful of is H2SO4. H2SO4 is one that's really important because the H3O plus, the H2SO4 is the first ionization, is the most significant, but second ionization cannot technically be ignored, all right? So when we think about H2SO4, we'll think a little bit more in class about how much H2SO4 is contributed, but it is not double and it is not exactly 1, all right? Because of its diprotic nature, H2SO4 starts off as a strong acid, and then remember HSO4 minus 1 will also contribute as a weak acid. When we get to weak acids, we'll dive into that a little bit more. Now, finding the pH of a weak acid, now we have to think about using an ice table. This is less than 100% ionization, which means that not all of that weak acid is going to react with the water. It's an equilibrium, right? This concentration of acid might be known, but in order to solve for pH, we need the concentration of H3O plus, which typically we don't have at the initial start. So to calculate the H3O plus concentration of a solution, it requires solving an equilibrium problem with using the ice table format. And it's using this reaction, H acid, HA is what we've been using, plus water yields the conjugate base, acid minus, and H3O plus. To solve for the H3O plus concentration at equilibrium, you will need a Ka and an initial concentration of acid. Let's dive into that, all right? We're gonna find the pH of a 0.1 molar HClO2 solution. Now, noting that this is a weak acid, we need an ice table, all right? HClO2 plus water, we will always use this equation, yields H3O plus and ClO2 minus 1. We will always use this type of equilibrium because we are going to be able to use the Ka in order to find our concentration. Now, when we look into this value, it's really important to make sure that we have our Ka table or some sort of a Ka value given. The Ka for HClO2 is 1.1 times 10 to the negative 2. All right, so let's start by preparing our ice table. We'll start initial concentration. We can just remove water from this whole thing because water, remember, is a pure liquid, so he's not going to be in the Ka expression, and we don't have any products to start off with. We know there has to be a change in concentration. We're going to subtract reactants and add products. We can tell that by looking at that we start with no products. And at equilibrium, we have these values. Now we can go ahead and plug these into our Ka. 1.1 times 10 to the negative 2 is equal to the hydronium concentration times ClO minus 1, ClO2 minus 1, excuse me, divided by HClO2. Now remember, water is not present because water is a pure liquid, so the Ka only includes aqueous things. As we keep whittling this down, what we do notice is that our Ka, just like our Ks prior, that Ka is not small enough to do the approximation rule. So we will have to do the quadratic formula, just like solving for equilibrium concentrations previously in chapter 15. Just because we're in acids now doesn't mean anything has changed. We are still going to make sure that we solve with the quadratic equation like before. So we should, as we carry over this denominator, I'm going to take away the times 10 to the -2 exponent idea, and I'm going to write it in decimal format because I think it's a little bit easier when I multiply it out. So I have 0.0011 minus 0.011x is equal to x squared. Bring all those over to one side, x squared plus 0.011x minus 0.0011. Again, A equals 1, B equals 0.00, oh, too many zeros, 0.011, and C equals negative 0.0011. We should be able to put that into the quadratic formula, and what we get out of that, the valid x, is 0.028. Since x represents our H3O plus concentration, that is the only value that we really would be interested in, the H3O plus concentration, because remember, that will determine pH. pH is equal to the negative log of that concentration. And so, what do we get? Type it out. 1.55. There is our pH for our weak acid solution. Things that you will have when solving for this type of problem. You will be asked to find the pH, and you will be given an initial concentration of weak acid and the Ka. Your job is to make sure that you know what the equation looks like so you can write the Ka expression and be able to perform the ice table. Okay? Now, increasing the initial concentration of acid results in an increase in concentration at equilibrium. So when we're looking at that relationship between H3O plus at equilibrium and our A initial, we can then calculate the percent ionization. All right, so going back to the values that we just calculated, just to make sure that we know, the percent ionization of HClO2 can be calculated as well as the pH when we have that ice table. Let's just go back and calculate the H3O plus concentration of our previous problem at equilibrium divided by the HA concentration initially. That was 0.028 divided by 0.10 times 100%. And we should get 28%, which means the weak acid HClO2, the weak acid that we just calculated the pH for, at 0.1 molar has a 28% reactivity. Means that 28% of our acid reacted. It's not a whole heck of a lot. That's why we call it a weak acid. All right, why doesn't the increase of H3O plus keep up with the increase of HA? Why can't we just keep adding HA and keep increasing the amount of H3O plus linearly? Well, we don't have that linear relationship. According to Le Chatelier's principle, if we reduce the concentrations of all the aqueous components, the equilibrium should shift to the right to increase the total number of dissociated particles. But the aqueous concentrations can be reduced by using a more dilute initial acid concentration. So we have some interesting ideas here with how do we get a larger percent ionization? Usually by adding more water, by making a more dilute solution and driving down that initial concentration of acid, we will result in a larger percent ionization. Because remember, the concentration of HA was in the denominator. If you make that smaller, then the magnitude of percent ionization will increase.